All right, so last video I talked about series circuits. In this video, I'm going to talk to you about a parallel circuit. So in a parallel circuit, what's interesting in a parallel circuit is that we have a common rail, both the negative and the positive. The common rail is both negative and positive. So basically what all these resistors, if we look at this as point A, this is all point A right here, and let's call this all point B. You notice that all in point A is that all my resistors are connected up to point A. Likewise, all my the other side of the resistors are connected up to point B. So in a parallel circuit, this is what you want. These are in parallel. So in a parallel circuit, the voltage, as based on your as readings and also in the lectures, should be the same throughout the circuit. So if I actually am going to zoom this out just a little bit here so you can actually see it. There we go. I'm going to move it over. So if I take and I measure, looks like I got to go a little bit more on this. Come on, focus up, focus up, focus up. Sometimes it just takes a little persuasion to get this thing focused up. So basically I have my parallel circuit still, and my meter. Turn the lamp on. Turn the lamp on. There we go. Set to DC. Okay, I'm going to set it for DC. So now what I'm going to do is measure across these leads. These are loads. So if I measure across, that's parallel, I should get the source voltage. It should be 5.3 volts. 5.3. 5.3. And 5.3. So now what we want to do is measure current. Now measuring current in this type of circuit requires takes a little bit of patience on it and a little bit of understanding. So in order to do that, what we have to do, and I'm going to see if I get this thing just to do it just a little better. There we go. My meter is right there. So what I want to do is measure total current first. So total current, I'm going to move this lead so you can actually see it. That's right there. I'm going to do is break that lead and put my red to red. And I'm going to put my black right to the power rail. I could actually connect it right there. You notice my meter said 9, and it said OL, and that's it's an overload on it. So basically, I was a little too low on it. I should have set it up higher. So in this case, I have 95.4 milliamps through this circuit right here. So the other way I could do that is take a wire, connect it up, 94 mils. So I'm going to keep this wire on my black. See, I put a wire on my black. I'm going to connect up my power back. Now, let's say I want to do a branch circuit. Well, this is where we want to take and use this wire that we put on the black, and we'll break the circuit. So the easiest place to break it is right in here. So I break it right there, take this lead and bring it up. So it's like, hey, I'm dangling there, help me out. So I need to reattach. So now I'm going to reattach, and now my reading is 58.7 mils through this branch right here. And I can continue to do that throughout all my branches. I'll do one more branch. So I just connect it up. And I have to be careful how much power I'm drawing through this, because through these load resistors, because in parallel, I'll talk to you a little bit more on parallel in a second, but parallel is that we see as more loads are added to it, more current is and more power is added to the circuit. So this one's 21.9 mils. Let me talk to you about this. This is 21.9 milliamps. So if we actually looked at how much power is actually drawn through that, if we take the 21.9 milliamps and we multiply it by our voltage, E or V if you want to call it, which is 5, it actually will give us our current, our power for this. So if we actually take this, and let's go to calculator, and if I take, say, 21.9 exponential plus or minus 3 times, remember, current times voltage is equal to power. So I take 5.3. I get 116.07 milliwatts of power through that. So that's actually close to a quarter watt. So we would actually use about a quarter watt resistor, which is about what we're using on there. So that gives you an understanding how to actually figure out power. So again, power is equal to pi. You look at pi, I times E, where I get E is the voltage across this resistor. E and V are interchangeable, so I can actually use those. I can use those two terms loosely, but be very careful in AC, because a lot of times in AC we use E instead of V. So if I wanted to check the power on this one, like I did it before, I'm just going to disconnect that, and notice I actually disconnected a branch. Not good, totally, but that's okay. If I take that one, I got 58.9, so I clear this out. I go 58.9 exponential plus or minus 3 times it by 5.3. I get 296.27. 296.27 milliwatts. So in that case, what I need is a quarter watts. That's a little short for that one. It's getting a little toasty there. So that should be like a half watt. So that should be a half watt resistor. So that's even though I think that is the one I'm using is close. I think most of these are all close to. I think most of them are close to a quarter watt I'm using right here. And I think that one should have been, and we should have went with a half watt on that one. So if you have any questions on this type of circuit, parallel circuit, please feel free to outreach to me. Hopefully this gives you a little better idea how to measure current and how to measure voltage, and also actually how to find power in a parallel circuit. Thank you.